Hello everyone and welcome to another video tutorial of the EMDLAB software. In this video, I am going to perform a magneto-static simulation using the EMDLAB software and also the ANSYS Maxwell software and compare the results. So here you can see the ANSYS Maxwell model of the switched reluctance motor that we designed in the switched reluctance motor design course. You can refer to the course videos, okay, and check the design process of this motor type. This case, this example has 8 stator poles and 6 rotor poles, right? The SRM 8 by 6, the rated power of the motor, and this is the rated speed of the motor. So we designed this motor before and we performed different analysis types: the magnetic loading analysis, calculation of the static curves, the dynamic simulation, and so on. Now I am going to do the same magnetostatic analysis using the EMDLAB software and learn how to generate the geometry, how to generate the mesh, and how to run the magnetostatic solver. So the first step is creation of the geometry. Let's generate the rotor geometry. You know the geometrical parameters of the rotor, right? So here, this is the width of the rotor tooth, and this is the arc of the rotor pole, the stator pole, and so on. This is the width of the stator tooth. This is the ISD. This is the OSD, outer stator diameter. And this is the shaft diameter. Okay. Also, we have this thickness, the width of the rotor yoke, and this is the width of the stator yoke. So, how we can generate this geometry? Like before, I define this geometry database, okay? And we need to define points. So this is P1 tag G dot at point. I generate a point at origin, right? So G dot show a sketch. Let's run the code. Here you can see this P1. So first, let's generate the geometry of the rotor. So if I zoom here and copy this image, okay, we can generate half of one rotor pole or rotor tooth. So we need 1 point here, 1 point here, 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 and here, and here. Okay, so we can generate this geometry. You know, because of symmetry, we can generate this geometry, right? Half of one rotor pole. Then we can copy and mirror the mesh. That is an efficient method. I will explain. So what is the coordinate of this point? Point number 1, 2. This one is actually here. Also, I need to define these geometrical parameters. The shaft diameter is equal to here. Let's check. 20 is the shaft diameter. The ISD is equal to 74. The OSD is equal to 125. The value of the air gap is zero point 0.5. Zero point 0.5. The value of the beta s, right? The stator pole arc angle and beta r is 19.8. So this is beta r. This is equal to 19.8 degrees. So because we defined this variable g here, so I changed the name of this variable to gap. This is beta s is equal to 17.1. Okay, so the second point is the shaft. To have a better code, I can write here, this is a global variable. Okay, so we will not have conflict between the names. So this is the shaft divided by 2. The y is 0. The next point, right, is actually global variable ISD divided by 2 minus global variable gap divided by 2. No, the gap. Okay, this point. So what is the x and y coordinates of this point? The point number 3, 4, 5, and 6. Here, this is actually this one times cosine of beta r divided by 2. So let me multiply this by pi divided by 180 to have it in radian. Okay, so this is beta r divided by 2. The y coordinate is the same, just this is sine. Okay, so this is P3 and this is 4. So now let's run the code. Here we generated these points. What is the next one? The x and y coordinates of this point number 4. Okay, so we need to know the width of the rotor yoke. Yes, the width of the rotor yoke is equal to 7.53. Okay, so global variable width of rotor yoke 7.53. So when we know this variable, actually if we know this angle, we can calculate the x and y coordinates of this point. So The angle, this angle, I call this gamma r. Gamma global variable, gamma r is equal to actually this angle, right? This is angle between this line and this line. This is equal to a sine of actually this one, the global variable ist divided by 2 minus gap, right? First, I need to calculate the width of the rotor tooth or the rotor pole divided by 2. Yes, divided by, right, this one to calculate actually this angle, gamma r. So here I can even define this variable, global variable width of rotor tooth, that is equal to this one times sine of global variable beta r divided by 2. Okay, so I'm going to calculate the width of the rotor tooth. This one is actually 2 times the radius, right? That is this one times the sine of beta r divided by 2. So if I run the code, let me check delta output argument, the gap. Yes, this is global variable gap. So if I run the code, this is the width of the rotor tooth, 12.55. Width of the rotor tooth, 12.55, right? The same as this one. So this is the gamma r, that is actually a sine of the width of the rotor tooth times zero point 0.5 divided by global variable d shaft divided by 2 plus width of the, right, rotor yoke. So when we know this gamma r, I can calculate the x and y coordinates of this new point. This is this one, d shaft divided by 2 plus this one times cosine of this variable, and copy paste it here. This is sine. So let's run the code. Yes, we have this point, 0.5, but it seems it's not correct. No, it's correct. Let's continue the design. So the next point is here. We can copy and paste this. The rotor pole pitch angle alpha p is 2 times pi divided by global variable nr, that is 6. Excuse me, the nr here we should define it. Global variable ns is 8, global variable nr is 6, the number of the stator poles, the number of the rotor poles. So here, this is alpha p divided by 2, and this is alpha p divided by 2, the point number 6, this point, and finally, we can define this point, right? This point. That is actually, I need to write this one, just D shaft divided by 2, the point number 7. So we defined these points. Now we can draw segments and arcs to generate the geometry. Here I add a new segment from P2 tag to P3 tag. So if I run the code, here as you can see, we draw this E1. So now we should plot an arc here. So this is add a new arc. The center point is P1T. This is P3, P4. Again, we have a segment. The direction of this arc is counterclockwise. This is from P4 to P5. So let's run the code. Yes, this arc and this segment E3. Again, we have arc from P5 to P6. A segment again from P6 to P7. And finally, another arc from P7 to P1. But if I consider it counterclockwise and run the code, yes, excuse me, P2. Yes, as you can see, this is counterclockwise, this arc. The number of points is low. If I increase the number of points, also g dot set mesh max length equal to 1 millimeter. Yes, this is the arc. But we know that this arc is clockwise, so we should set this number equal to 0. So if I run the code, here we have the geometry of the rotor pole. So now I can define this loop. You know that here I write loop 1 tag is g dot add loop. This is a new loop, so we can use these tags also. This is E1 tag to get the tags of these objects. E2, E3, E4, 5, and 6, right? So this is E1 tag, direction is in the same direction of the loop. Yes. So here, let me plot the sketch again. So I am going to define a loop. So here, we are going to define this loop, right, in this direction. So this is the direction of E1, E2, E3, E4, E5, and E6. All of them, right, are in the same direction of the loop, counterclockwise. We know that the direction of the loops that we define should be counterclockwise. So here E2, E3, E4, 5, and 6. Okay. So finally, I can define this phase. G dot, add a new phase. This is the rotor L1 tag. This is the loop. And let me copy the code here. Then we need to generate the mesh. And then we can show the mesh zones. M dot show mesh zones. So if I run the code, as you can see, we generated the geometry and this is the mesh. So now we can use this auxiliary function. When we generate the mesh, I can use this auxiliary method to construct the full geometry of the rotor. M dot auxiliary copy rotate join mesh zones, right? So here we have these inputs. The mesh zone name is the rotor. So here, let me, yes, use this function. This is the rotor. This is global variable nr, global variable nr. Okay, so if I run this code, as you can see, we have full mesh of the rotor. But what is this auxiliary function? In this method, first we mirror the rotor mesh zone with respect to the x-axis. Then we rotate the full geometry, right, nr times. So we need to know the shift angle and the number of, right, shifts, rotates that we need to consider. So here we need to consider these two numbers that are the same. Here, if I write 3 and run the code, as you can see, only I have 3 poles. But because I need to generate the full geometry, I write global variable nr. You know that sometimes we have symmetry and we can simulate just one pole or one fraction of the motor. So, yes, this is the rotor geometry and we can set the color here also, the color of this mesh zone. So, you can see the quality of the generated mesh also. Now let's generate, right, the geometry of these regions of the rotor, these rotor air pockets actually. So how we can generate that geometry? We need to define this segment. Okay, here we need to define this arc, excuse me, and also this segment. Yes. So we need to define this point actually. Here I need to define P8 and this is P8 tag. Here we have the global variable ISD divided by 2 minus gap instead of this and here. So after defining this point, let me highlight this part of the code. When we define this point, we can define this arc and also this segment. So this arc between P4 and P8. So here I define this arc E7 and this is E8. Add arc from P5, this point, to this point, P8, and from P8, this is counterclockwise. We need to define a segment here from P8 to, actually, let me check. This is P8 to, the direction of the arc is important. Let me check the sketch. So this is P2, P3, P4. So here, this is P4. Yes. And this is from P8 to P6. Yes. This air pocket. Okay. So here for this region, we need to define a new loop. Okay. How we can define a new loop? So here we defined this loop for the rotor before, and here we have this reference loop counterclockwise. We know that the direction of this edge is in this direction, E8. This is E3 and this is E4. So the direction of the E3 is in opposite direction of the loop, right? So here, when I define L2 loop, I have these edges E3, 7, 8, 4. E3, 7, 8, and 4. But I know that this is in opposite direction, this is in opposite direction. So here I have this one. This is the rotor air pocket. I write. So now let's generate the mesh and check. Show mesh zones. Yes. This is the rotor core and this is the rotor air pocket. Again, I can use this function, the rotor air pocket. Yes. Copy mirror join mesh zones. And here, as you can see, we have the rotor core and these regions. We can generate the stator core and the stator winding. Then we can define the air gap in a similar way. So this is the geometry, m dot show geometry. Let me set the color of the rotor air pocket. I'm going to select this color, 200, 191, 231. This is the rotor air pocket. 200, 191, and 231. Yes, the rotor core and these regions. Now, how we can generate the geometry of the stator core, right? Using a similar method. Here, let me copy these three variables. I can write the width of the stator tooth is the ISD divided by 2. This is beta S. Gamma S is the width of the stator tooth. And this is the global variable OSD minus width of the stator uke. This is the alpha of the rotor pole, alpha of the stator pole. This is an S. Everything is the same. Okay. So now I can copy these lines, use them here to generate the stator. So here I don't need to define this again. Yes, this is the ISD divided by 2. Okay, let me highlight these lines just to run the code and check. So this is ISD divided by 2. This is the OSD divided by 2. We don't have this gap. Actually, I am generating this part of the stator core. Okay, so here we have this part of the stator core, this point, this point, this one, this one, this one, and this one. Okay, so here this is the point, first point, the second point, and so on. So here this is the OSD divided by 2. This is the OSD divided by 2 times this angle, alpha stator pole divided by 2, and this is sine. So we have this point here. We need to define this point. So here, just I should subtract the global variable width of the stator uke. So if I highlight these lines, just run the code. We don't have global variable width of the stator uke. Yes, this is the width of the rotor uke. The width of the stator uke is here 7.7. The stator uke 7.7, and we defined these points. Okay, so the next point is this one. We have this radius the same. This is the global variable is the gamma s, actually divided by 2. No, this is just gamma s. Okay, so let's run the code. Yes, let me check. The global variable gamma s is here. Width of the stator tooth divided by 2. The outer stator diameter divided by 2 minus the width of the stator uke. So this is the point. So if I run the code here, P13 should be actually here. in this region, right? So, what is the reason? What do you think? This is the gamma S. Okay, this point. And finally, we have the ISD divided by 2, ISD divided by 2. This is the beta S divided by 2. So this is beta S and this is beta S. Okay, we defined this point. This is P9. What is the radius? Is the ISD divided by 2. ISD divided by 2. This point, 14. Okay, so again, I can generate the segments, similar to this one. This is the same. If I run the code, here we have these segments. Let me check from P2, right? This segment. Then we have this arc. Yes. Then we have this segment. Then we have this arc. This is counterclockwise. Okay. Then we have this segment. Yes, this segment. And finally, we have this arc. So, this is the stator. And again, when we define these tags, I can call this L3. The L3 is the stator. L3 is the stator. So let's generate the mesh also to check. This is the stator mesh. Similarly, we can set the color of the stator mesh and use the same function that we had here. This is NS. So we have this detailed code and we can handle the mesh later. And as you can see here, we have a perfect mesh for the stator and the rotor. We need to create the geometry and mesh out the stator winding also. Here, let me check other functions. M.show mesh. This is the global mesh. Yes. M.show wireframe mesh. This is the wireframe mesh, and so on. Let's create the stator winding. Here, we need to define this point. This is ISD divided by 2. ISD divided by 2. This is the stator pole. We should define this segment. Okay. So let me run the code. The segment is from actually P12 to P15, this point. So is actually, I can write the exact tag, or find the related tag. So here, the tag of this point is P12, this is P15. So I can write here P12, and this is P15. Okay, this edge, and finally this arc we need to define. This is 0 from P15 to P14. Okay, this arc. So how we can define the loop for the coil arm? Here we should define this loop. We know that this is the reference direction of E12, E13. This is the reference direction of the E16 and E15. So here I write this loop L4. This is E13, E12. This is 0. We have this tag. I write different codes just to explain the method, but you can consider a unique procedure. So E12, E13, E12, E16, and finally E15. These are in the direction of the loop. So here I define this one, the stator coil arm 1 L4. So here, as you can see, we defined the geometry of this coil arm. Then we can mirror and rotate this geometry. Then we need to define the air gap mesh to have a high quality air gap mesh and continue the analysis. So because the time of this video is high, let's pause here and continue in the next video. Thanks for watching.